In this lesson, we are going to talk about algebra and composition with functions. And basically, that's when we look at how to combine and manipulate and analyze functions to solve problems. This is the chapter opening. It gives a situation where you have a function based on the number of plastic bottles recycled, the number of water bottles sold, versus the temperature. And what we're going to get into later with this example is how each of those can depend on each other. So we know that temperature might change how many water bottles we purchase, right? In the summertime, we might buy a lot more water bottles. So the number of water bottles is going to depend on the temperature. And then if we want to see how many plastic bottles are recycled, we need to know the number of bottles that are sold. So that's this function. So it's going to show us the relationship between these three quantities. So let's first start with the rules for the algebra with the functions. So we have 4 rules here on how we can add, subtract, multiply, and divide functions to create new functions. So this first rule is that we're adding f and g together, those two functions, to create a new function. And we can call it whatever you want. You can call the new function h of x or whatever you'd like. And we just simply add them together. On the left here, you'll see that this is the notation for adding f and g. It's literally the name of the function, just like if we have f of x, we said that this letter f is the name of the function. Same thing, and this is our input. Now we have 2 functions that we're combining, so f plus g is the name of the function, and then there's our input. So we have different notation that we're looking at here. Now the same thing goes with subtraction. If you want to subtract 2 functions to create a new one, it's just when you take f of x minus g of x. Then if you want to multiply 2 functions to get a new function, this is the notation you're going to use for multiplication. And then same thing for division, you want to divide. However, when you divide, you want to make sure that when you're combining functions, you state what would make 0 in the denominator. So when you combine to make a new function, you want to make sure that you're checking your domain. When you do division, you want to make sure you state that g of x cannot be equal to 0. Now, a couple things to take note of. Just like when we're adding or subtracting, multiplying, or dividing with numerical values, f plus g, that new function, is commutative. So if I put in f plus g and I add them together, that's going to give me the same function as if I add g first, g plus f. However, with subtraction isn't commutative, so if we subtract in the wrong direction, we're going to get a different function than what we intended. So if it's labeled as f minus g, so you have to take f of x minus g of x, you want to make sure that you maintain that order. And then with division, of course, that's not commutative. If I take f divided by g, and then I take g divided by f, those are not going to be the same. There's a note down here that the author made. Sometimes students get confused and think that this notation means to multiply. Sometimes students see that and think that you need to distribute and write that as f times x plus g times x, and it's not the same. If you take the function and multiply it by x, all your exponents for the x's are going to go up by 1, and it's going to give you a different function. Same thing with this. This notation does not mean to distribute. It means you're adding 2 functions together, and this x is just the input. No, it doesn't mean to multiply by x. Okay, let's look at our first example. We have f of x is 4x minus 3. we have g of x is 4x squared minus 7x plus 3, and h of x is x minus 1. And we need to find f plus g of x. We need to find f times h. We need to find f times g of x, and then g over f of x. And we're going to use the functions that are given. Okay, f plus g, for this first example, we're literally just going to take the two functions, f and g, and add them together. So we have 4x minus 3, that's f, and we're going to add g, which is 4x squared minus 7x plus 3, and that's our g. So when we add them together, we can combine like terms. So when we combine like terms, our final answer is going to be 4x squared minus 3x. Now for f times h, we're going to take f of x, which is 4x minus 3. This is our f. And we're going to multiply that by h, which is given as x minus 1. So here we're going to use the distributive property twice because we have two binomials that we're multiplying. So I'm going to take 4x times x and then 4x times negative 1. Then we're going to take 3 times x, or negative 3 times x, I should say, and then negative 3 times negative 1, and then combine like terms. So when we work that out, we're going to get 4x squared minus 7x plus 3. All right, now we're going to do f times g, not f times h. Okay, f is going to be 4x minus 3, and I'm going to multiply that by g. So here's my f, here's my g. I'm going to multiply by 4x squared minus 7x plus 3. We have to take, or the 4x times the 4x squared times the minus 7x, and then times the 3. And then do that same thing with the negative 3 as well. And then when you combine all of your like terms, you will get 16x to the third minus 40x squared. I'm going to continue down here. I'm running out of room. Let's see, 40x squared, and then plus 33x minus 9. For the last one, we're taking g and dividing by f. So we have g, which is 4x squared minus 7x plus 3. And we're going to divide by f, which is 4x minus 3. Now, we can do this by factoring, or we can use long divisions with, we can do this by factoring or by using long division with polynomials. I think factoring, for me personally, would be easier if it factors nicely, and in fact, this one does. If it doesn't factor nicely and you need to simplify it, then I would use the polynomial long division. So the 4x squared minus 7x plus 3, that factors as 4x minus 3 times x minus 1. And then we're going to divide that by 4x minus 3. So when we simplify g over f of x, we get x minus 1. Now, if I graph g over f, I'm going to get something that looks like it's going to be a line. It's going to be x minus 1 when I graph it. However, you have to notice that 4x minus 3 is in the denominator, so I have to look to see what makes that 0. If I set 4x minus 3 is equal to 0 and solve, I'm going to get that x is 3/4. So I cannot plug 3/4 into that function. Even though we simplified it to x minus 1, if I were to plug 3/4 in here for x, and then I find g of x and divide by f of x, I'm going to run into a problem at 3/4. Let's take a look at this so that I can show you what that means. I'm going to pull up GeoGebra. Now, when you look at these two functions separately, we know that this is going to be, for both of these, the domain is all real numbers. Because when we look at G, that's a quadratic. And when we look at F, that's a linear function. And I can plug anything I want into either one of those and not run into any issues. But when I combine the functions into a new function, that's when we're going to run into a problem. So if I create a new function and I tell GeoGebra that I want to make a new function and call it G of X, let's see, and I want to divide f of x. Okay, we got this new function here. I'm going to turn off the other two now so we can look at just the combined function. So I'm going to tell the calculator to evaluate h of x at 3/4. And you'll see that we have no value. There's an asymptote there. And there's an asymptote there because we get 0 in the denominator. However, if I plug in 3/4 into f of x by itself, I can plug in 3/4 there and I'm not going to run into an issue. In this second example, we're going to take the new functions from example 1 and we're going to evaluate. So I'm going to take f plus g and plug in 2. Based on our new function that we got, we have, let me highlight this, we have 4x squared plus 3x, and we're going to plug in 2 to that. When we do, we're going to get 4 times 2 squared minus 3 times 2, and then we're going to get the value, once we simplify that, as 10. Let's see, the next question says find f times h of x, and we need to plug in -1. Let me actually put that in there. Okay, so I'm going to take -1 into our f times h. When we do that, we're going to get 4 times -1 squared minus 7 times -1, and then plus 3. When we simplify that, we're going to get 14. Now let's find the next one, which is f times g of 0. So let's see. That's this one right here. So when I plug in 0, we're going to get 16 times 0 cubed minus 40 times 0 squared plus 33 times 0 minus 9. When we simplify that, that actually is nice arithmetic because it's less work. All the first 3 terms are 0, and then we're left with just -9. Last one. We're going to do g divided by f of x. And we're plugging in 5. Okay, when we plug in 5, when we simplified the function, we got x minus 1. So when I plug in 5, I get 4. Just remember, if you're asked to plug in x is 3/4, that's going to be undefined. Even though it looks like we can plug it in here, it's not going to work. So just keep that in mind. That's why it's really important to write down those restrictions when you run into them. So now let's talk about how we can use the algebra functions to create new functions and how it can be applied to business. So the most common formulas in business is the one for profit, and then we have revenue and we have cost. Notice that the profit function is made up of 2 other functions. To come up with the profit function, we need to take the revenue function minus the cost function. And here are all those functions together in one graph. The revenue function is based on the number of items sold times the price of each item. So for example, if there were 100 items sold for $9 each, that would be 100 times 9, which would be a revenue of $900. But if there were 500 items sold for $11 each, then we would have a different revenue, which would be 5,500. So when we look at the revenue function by itself, it's going to be X times the price function. Because the profit is P also, I'm going to actually name the price function because it's short. I'm going to take and name that price function price. That way we don't get confused with the profit function. So in general, if X is the number of items sold, let's write that down. This is our X. This is our price. Let's look at example 3 now. A manufacturer of hard shell cases for the iPhone knows that the number of cases she can sell each week is related to the price of the cases by the equation X equals 1,300 minus 100p, where X is the number of cases and P is the price per case. So this is one of the formulas that we're probably going to need. It says P represents the price and X represents, let's write this down, the number of cases sold. P is the price. And the last sentence says, what price should she charge for each case if she wants the weekly revenue to be 4,000? Now, typically in a word problem, you're given a lot of information throughout the body of the question, but usually the last question states specifically what the author of the question wants you to find. So they're asking to find the price when the weekly revenue is 4,000. So we have find the price, which is P, when the revenue, specifically I'll put under here weekly, is equal to 4,000. So we need to come up with some kind of equation for the revenue so we can solve the price when the revenue is 4,000. Now, we know that the formula for the revenue is we take the number of items sold times the price. So we have X times P. X is the number of cases sold, and that is given to us in the question. So I can rewrite this as 1,300 minus 100p. So this was our X. Let me color code this for you. So this was our X. This is the X that was given to us in the problem. And now we have to multiply the X times the P. We don't have any information for P. All we have is the variable P. So we're just going to write that down. So here's our P. And I just brought it down. So now we have a formula for the revenue. So I'm going to put 4,000 in there and solve for the price because that's exactly what it's asking us to find. Find the price when the revenue is 4,000. So I have 4,000 is equal to 1,300 minus 100. Actually, let's just distribute while we're doing this. So I have this times P. So when I distribute, I have 1,300 times P minus 100 P squared. So now what we have to do is solve this equation for P. That's what the question was asking us to do. This is a quadratic, so we have different ways to solve a quadratic. We have factoring, quadratic formula, complete the square method. We have all different kinds of methods. I personally think that factoring is the easiest if you can do it. But if you can, or you don't like factoring, you can use one of the other methods. I'm going to use factoring. And another thing is, before you start trying to solve, you need to set up the quadratic so everything's on one side and 0 is on the other. So I'm going to add 100p squared, and I'm going to subtract 1,300p from both sides. So that's going to give me, when I put it in descending order as well, that's going to give me 100p squared minus 1300p plus 4000 is equal to 0. So here's our quadratic that we need to solve. It's set up now so that it's equal to 0. I'm going to try to factor first. Now I notice that there's a 100 in front here, and I have all of these values that are divisible by 100. So I'm going to factor out the 100, and then what's going to be left is p squared minus 13p plus 40 is equal to 0. Now I got to think about what are factors of 40 that would multiply to give me positive 40, but add to give me a negative 13. So you're going to have p minus 5 and p minus 8. So my price is going to be 5, or my price is going to be 8. This means that if the price is either $5 or $8, she will have a weekly revenue of $4,000. So let's write that down. $5 or $8 will give her a weekly revenue of $4,000. Now we're going to talk about composition functions, which is another way to create a new function from two or more other functions. And this is the example that we talked about at the beginning of the lesson. Let's go into this more deeply and see what's going on here. So recall that the situation was that the temperature, when the temperature changes, the number of water bottles that are sold will change, which then changes the number of plastic bottles that are recycled. So the number of plastic bottles recycled depends on the number of water bottles sold, and the number of water bottles sold depends on the temperature. So this is the symbol for when you're doing a composition of functions. Some people get that mixed up with multiplication because they see it as a dot, but it means something completely different. If you see this dot as an operation, that means composition, not multiplication. Okay, now the way a composition function works is that you're taking and evaluating a function using an entire other function. So rather than plugging in a number and evaluating, you're plugging in another entire function. So you've got a function within a function. If you have f of g of x, that means we're plugging into g of x first and then evaluating it with the function f. So I plug into g, this is my g function, and then I take the answer from the g function and plug it into f. So I'm plugging in an x, and it's working through the g function and then the f function. When we look at this example down here, this is g of f of x. This means I'm plugging in a value into f first, and then taking that answer and applying it to g. So here's my x, it's going into the function f, and then the answer from your f of x is then going into g. And so then your value comes out as g of f of x. This is very important that you understand this. Composition is not commutative. In other words, if I plug in g first and then apply it to f, that's not necessarily going to be the same as if I plug in f first and then apply it to g. Sometimes you might have some special cases where it's a coincidence that those values are the same, but typically they are not. It's not guaranteed that these two are equal. Okay, so commutative property does not apply to composition functions. Let's look at example 4 and apply this now. We're given that f of x is equal to x plus 5 and g of x is equal to x squared minus 2x. We're going to find f of g of x and g of f of x. One thing when I was learning this, I would always get confused on the direction. So one thing that helped me remember what got plugged in first is when I wrote it out, let's write out this one first. Because the f over here is on the left and the g is on the right, when I rewrite this, f is going to be on the left just like it is here, and g is going to be on the right. And that helps me figure out what I plug in first. This is telling me I plug g of x into f of x. So that means I am going to take this whole function right here and plug that into f of x everywhere I see x. So here's my f of x. I'm going to leave room here. Here's my f of x. So I need to plug in g of x everywhere I see x. So that's here and here. So I have x squared minus 2x. That's my g. And then I put g in for this x as well. So I get x squared minus 2x. That's my g, and then I add 5. Then once you get that, you're going to want to simplify. So when I combine them, I have x squared minus 2x plus 5. This will be my final answer. And that is f of g of x. Now when I do the other way around, when I do g of f of x, so this tells me that I'm taking f of x and plugging it into g. This is the input. It's the whole entire function. So when I write out g of x, I'm going to leave room again. So my g of x is x squared minus 2x. So I'm going to take x plus 5 and plug it in. There's my f of x. I am going to put x plus 5 here. This whole thing is going to be squared. Minus 2 times x plus 5. So I'm going to have to square the x plus 5, which means x plus 5 times x plus 5. And then I'm going to subtract 2 times x plus 5. Remember to distribute that minus in front of the 2. And when we simplify that, we get that g of f of x is x squared plus 8x plus 15. So now we're going to talk about an example or an application with how temperature and recycling relate. That was similar to what we talked about at the beginning of the section or the lesson. In example 5, it says, suppose that for temperatures greater than 10 degrees Celsius, the average number of soft drinks sold each day, which is S, that's what they're calling the drinks sold, and that's going to be in hundreds. It's important to pay attention to those details. And it depends on the temperature T. So here's our function right here that tells us the number of soft drinks sold at a given temperature, T. And then we're given the number of soft drink aluminum cans that are recycled. We're going to call that R in hundreds. And that depends on the number of soft drinks sold, which is S from the function above. So we're going to work through these questions here. The first one is give some reasonable numbers for the domain of the function S. Part B is how many cans are sold when the temperature is 27 degrees Celsius. Part C is how many cans are recycled when the temperature is 27 degrees Celsius. And part D is, suppose we want to use Fahrenheit temperature scale instead of Celsius, how would the problem change? Okay, so let's work on all of these parts. So for part A, we talked about previously that people tend to drink more soft drinks. Before we were talking about water, but they tend to drink more on hot days than on cold days. So we're going to restrict the domain for this function so that T ranges between 20 degrees Celsius to, let's say, 40 degrees Celsius. And when we're talking about that in terms of Fahrenheit, that would be about 68 degrees Fahrenheit to about 104 degrees Fahrenheit. So between these two temperatures, it would be reasonable to expect that the number of soft drinks go up somewhere in that range because it's getting warmer. It's not cold like in the 30s or the 40s anymore, and people might be drinking more. So that would be a good input or a good domain for our model. Part B, to find the number of cans sold when the temperature is 27 degrees, we're going to substitute 27 in for T and use our formula. But the question is, which formula do we use? Remember, the question is asking for the number of cans sold. So that's our function S. Be careful not to plug it into the wrong equation. That's why it's really important to understand what your variables are representing so you don't plug it into the wrong one. Up above, we had that the number of soft drinks sold was 1,200 plus 23T plus 600 times T minus 10 raised to the power of 1/3. So we're going to plug in, for this one, it's saying when T is 27 degrees Celsius, find the number sold. So we're going to plug 27 in for T, and we're going to get 1,200 plus 23 times 27 plus 600 times 27 minus 10 raised to the 1/3 power. When we evaluate this, we're going to get that S of 27 is approximately 3,363. Remember that both functions were given in terms of 100, so I have to add 2 zeros on this to complete the answer. So I would say that since S represents hundreds of cans, the number of cans sold is about 336,300. And that's because S is in hundreds. Okay, let's look at part C. Part C said how many cans are recycled when the temperature is 27 degrees. And our function R is the numbers sold. You plug in the numbers sold to the function R, and then you take the numbers sold and you raise it to the 3/4 power. So the number sold is 336,300. However, remember, R and S are both in hundreds, so I don't want to put in 336,300. I want to put in 3363. So when I plug in 3363, and I raise it to the 3/4 power, we're going to get approximately 442 for that answer, but that's in hundreds. So when I write out the final answer, I'm going to put that R is in hundreds of cans so that the number of cans recycled when the temperature is 27 degrees Celsius would be about 44,200 Kangs. This is Kangs sold. This is Kangs recycled. Okay, the last question, part D, says, suppose we want to use Fahrenheit temperature scale instead of Celsius scale. How would the problem change? Now, because S of T is in terms of Celsius, T represents the degrees Celsius. So I can't directly plug in the degrees Fahrenheit there. So we're going to have to add another function at the beginning of this chain of functions to turn degrees Fahrenheit into Celsius. So let's add a new variable. I'll call it F for degrees Fahrenheit. And so we're going to have to take our function, degrees Fahrenheit, and plug it into this S of T. So that way the temperature in degrees Celsius is going to depend on the degrees Fahrenheit. So, and that function is going to be 5/9, and we're going to take Fahrenheit, whatever our degrees in Fahrenheit is, and subtract 32. That's what we're going to plug into our S of T. So now we have 3 functions that we're plugging in. So this is going to look like, so up here, let me clarify so that we can kind of follow what's going on here. I have to take S of T from part B to C. I need to take S of T and plug it in to R. So that means this is a composition function where we're doing this. So I'm taking R of S of T. That's what's going on here. But now because we're adding a third function in there, we have to take F and plug it into S first to change the degrees of Fahrenheit to Celsius. Now we're going to have a composition of 3 functions. When we add that third function in our F, we're going to have to do a third nested function. So what we're doing is now is we're going to do R of S of F of T. So when we write that out, it's the same as what we did before. We're just going to write it with a third function. Since R is on the left, S is in the middle, and F is on the right, it's going to look like this. So now in example 6, we're going to practice composition functions again and evaluating it at x equals 2. And even though the question doesn't ask here to do this as part of the question, I'm going to go through and show you about finding the domain of composition functions because these can be a little bit tricky too. So the first thing we're going to do is find f of g. Because f is on the left, here it's going to be on the left in the new notation, and g is going to be on the right. So f of g of x. So that means I'm plugging in g of x into the function f. So this whole thing here, 2x plus 3, is going to go into that x, because that's the x in function f. So I'm going to have f of g of x is going to be equal to the square root of 2x plus 3. That was my x in f of x, but I'm replacing it with 2x plus 3, and then I still have that minus 3. Now when I simplify, that's going to give me 2x, because the 3 and the minus 3 adds to 0. I want to make sure that 2x is going to be greater than or equal to 0, which means x is going to be greater than or equal to 0. Now I can check it by looking at the functions. This is saying x has to be greater than or equal to 0. If I plug in something that's negative there, let's say -2, then I'm going to get 2 times -2, which is a -4, and I add 3, that's going to give me a -1. Now, when I take that answer and plug it in here now, I'm going to get -1 minus 3. So that's going to give me a negative number under the square root. So I need to make sure that whatever I plug in for x here is going to be positive. So for this new function, f of g, we're going to say that the domain is from 0 to infinity. So now if I actually go ahead and plug in, because that's what the question asked, evaluate this at 2, I'm going to get the square root of 2 times 2, which is the square root of 4, which comes out as 2. Now, this last example, I want to discuss this classic example to show you why looking for the domain with composition and addition, subtraction, multiplication, division, when we look for the domain of the new function, it can be kind of tricky, especially with composition functions. You have to really think about what you're plugging in and what's getting plugged in first and then what's getting plugged in second. So if I let f of x be the square root of x, and I let g of x be x squared, then we're going to find f of g of x. And then over here, we'll make some space. We'll do g of f of x over here. So let's look at this one first. I'm taking g of x and plugging it into f. So that means this is going to go in here for that x. So that means I'm going to take the square root of x squared. That's going to be f of g of x. Now, it looks like I can simplify it and get just x, right? The square root of x squared is x. However, when you look at the graph of this, you're actually going to be surprised. The domain is all real numbers, but it's actually not the graph of x. It's actually the absolute value of x. And this sounds a little bit strange, but let me explain it to you if you haven't seen this before. So whatever I plug in for g, that's going to get squared. So whether I plug in a negative or a positive, it's going to come out always as positive because of the square. And then when I take the square root, when I do the second operation with the square root, it's going to undo what I just did, and I'm going to get the positive value of whatever I plugged in for x. So for example, if I plug in -4 here, it's going to square it and come out as positive 16. And then I'm going to put positive 16 in here, and it's going to come out as positive 4. So no matter what I plug in here, negative or positive, it's going to come out as that squared is positive, and then the square root undoes it. But when I take the square root of a positive number, it's always going to come out positive. So when you look at the graph of f of g of x, even though it looks like it would simplify to x, it's actually going to be the absolute value function. And I'll show you just in a minute with the GeoGebra. Now for this one, I'm going to take f of x, which is this, and plug it in for this x. So when I do that, I'm going to get the square root of x, and then this is going to be squared. And again, when we simplify that, we think that it's just going to be x. However, remember, I can only plug in 0 or positive numbers under an even root if we're dealing with only the real numbers. So whatever I plug in for this is going to be greater than or equal to 0. And then the g of x is just going to square it. So all of my values that are going to come out are values that are greater than or equal to 0. When we simplify this, it is going to be a line. However, it's going to be the line y equals x with a restricted domain. It's going to be y equals x where the domain is only x is greater than or equal to 0. So I plugged in the values previously. We have f of x is the square root of x, and we have g of x is x squared. So these are what I like to call the mother functions. And now if we call it a new function, h of x, and we find f of g of x. So it looks like it simplifies to just x. However, because everything comes out of that as positive, we're going to get the absolute value of x. Now looking at it in the other direction, our new function is called p of x. We're going to plug f of x into g of x. So that means I'm going to have the square root plugged in to x squared. Now remember we said it's going to be a line y equals x, but with a restricted domain. We cannot plug in anything that's less than 0. So when I graph that, you can see it's the line y equals x. However, it's showing x is equal to 0 and up for the domain. So if you want to graph a composition function or one of those addition, subtraction, multiplication, or division functions, and you want to see what those combined functions look like, you don't want to put in the simplified version. Because if I just put in x, it's going to show the whole thing. It's not going to show me what the composition function is. So if you want to see what the new function looks like, define the two functions first and then plug one into the other. And then you can see truly what that new function looks like. So to close out this section, self-check. These are some questions you should be able to answer after you start practicing the problems and you look through the lesson video. Let's see, part A says, how are profit, revenue, and cost related? We talked about that at the beginning. So just a quick refresher, profit is revenue minus the cost. And we know that revenue is equal to the price times the number of products. X is the number of products. Okay, so for part B, it says, what is the difference between f times g of x and f of g of x? So what this question is getting at is this is composition and this is multiplication. Another way you can see the multiplication, you might see it with a dot like that, which is fine, but if it's an open circle, that's composition. So don't get confused with that. And remember another thing, that composition functions are not commutative. That's really important. Let's put that down as part E. Composition functions are not commutative. In other words, f of g of x and g of f of x are not typically going to be equal. There may be some special cases where it does, but it's not guaranteed. Part D, it says, how do you find the domain of a composition function? And we talked about that quite a bit. You don't want to look at the simplified version. You want to look at the unsimplified version to see what you're plugging in first and what comes out so that you can kind of determine what that domain is. And then you can always check it on GeoGebra by plugging in the f and g functions and graphing f of g or g of f. Composition functions can be a little bit tricky, but once you start practicing, it'll be fine. And then if you have questions, let me know. This composition idea, when we start talking about the calculus topics, when we take the derivative, we're going to use this idea of composition functions when we start talking about something called the chain rule.